That's better. Thank you. So before I want to start about the method, I would like to talk a little bit about how we came to work on that. And that is, we were asked to look into how we could detect malware that's using image files to communicate. And well, like everybody else, we would. So that was basically all the information we had. So we started to design a scenario under which, well, this detection made any sense. So we came up with something like this. So a medium security facility where you have high value information being worked on in a secure network, and the system in such a network usually don't have direct internet access. But you do have access to systems in a demilitarized zone, so where a few systems reside that have access to untrusted networks like the internet. And the systems will only allow communications after the communication passed some checks. So they try to avoid, for instance, malware communications from taking place or sensitive data being exfiltrated. So in such a scenario, if you have a malware infection, it will be on a system that is in a protected network, and it will try to communicate with a system which is outside to, for instance, exfiltrate the data that it harvested from the machines. So now we had a good understanding of what the scenario would be. So if we could detect at this, let's say, web application firewall, the fact that malware communication is taking place, we could prevent it. And so we started to look into the literature, what kind of methods are used to hide information in images. And turns out everybody is looking at how to detect information that's being transferred in JPEG coefficients. So we've been working on that for quite a while, and then we thought, okay, now let's check how's malware actually using? What algorithms are they using? Is it F5? Is it model-based steganography? Are they using outguess or maybe their own algorithms? And turns out that when we did another survey on that, the picture turned out to be quite different. So here on the left-hand side, you have the column for JPEG, so that's actually the most prevalent format. But as you can see here on the top, you have the approaches that use the file structure rather than the image data. And turns out that that's actually the most prevalent method. When you look at other formats, well, the focus shifts a little bit towards the image data, but you still have a high fraction of malware families that use the structure of the files rather than the image data. So we were thinking basically, okay, we must have been doing something wrong in our first survey. So we did a very large reiteration on that. We tried to broaden the scope, make really sure that we don't miss anything. And turns out that no, we basically catch the gist of it. So there's a lot of research on detecting steganography in media data, but there was actually no published paper on detecting, basically data exfiltration in the structure of files. So we thought, okay, well, this seems to be a really relevant problem in practice, but we don't see any work on that being published. So we thought, okay, we really have to get into this. And before I can tell you a little bit about the method that we came up with, I just have to briefly go over some basics. So first is to, basically create a compressed image file. You start from, let's say, some raw image data. And then there's an encoding process that takes place. And then the outcome of that will be encoded image data. But for a decoder to be able to interpret the data, it usually needs some extra information, let's say metadata or decoder data. And obviously, so you want a decoder on the receiving side to be able to decode the image. So you have to add that data to the image data when you store it in the file. So a file often looks like this, like what you see on the bottom right. So you have a series of segments that contain some data, and usually the largest one is the one that carries the image data. But you also need this other data to be able to decode the image. So this is how it looks like when you hide data in the structure of such a file. So starting with the clean file on the left, that's the same that we've been seeing before. The most simple approach is just take that file and dump some data at the end of it. And it works because, let's say, at least for JPEG and PNG files, they have a marker or a segment that indicates now this is the end of the image data. And the decoder will just stop reading the file after that. So it's a very simple, straightforward method to hide data, and it's actually used by high-profile malware. There's another method that you can see, segment injection, that requires a little more understanding of the file format. So, well, the most obvious segment type to abuse is a comment. So you'll just have a type of segment that's not interpreted by a decoder, so it will not have any effect on the decoded image, and you just put the data that's being transferred into that segment. And finally, you can use byte stuffing. So here you'll have basically a legitimate image, and you'll just take a segment that's legitimate in all respects, but it has to have true properties. One is that it has a length field, and the other is that the structure of the segment is fixed from a decoder's perspective. So what you can do is you just increase the segment length to, let's say, 100 kilobytes, and the decoder will usually have like two pieces, an outer piece that identifies, okay, there's a 100 kilobyte segment, and we'll call a subroutine that says, okay, this is a type A segment, so I'll parse that, and we'll read, let's say, 20 bytes from it. So the remaining 100, almost 100 kilobytes, that's where you can hide your payload. So that was basically what we were after. Just to give you a few cornerstones, so let's say one of the main steps towards solving this was that we said, okay, we'll interpret this file format as a formal language. And as you can easily see, that's an approach that's not really putting much requirements. So we have to have a structured file type that we can parse basically into a series of type segments with a length. And we implemented that for JPEG and PNG, but it doesn't even have to be a graphics file for this to work. And then we take training data, hi James, and build an approximation of that language. And what we do then is we match against this model, take into consideration that we have an imperfect impression of what the formal language looks like. And also, we want to add some restrictions so that we are not overly permissive. So when we'll use the threshold tau, which is just a minimum count of observations during our training phase, and factor alpha, which I'll go over in a minute. So since we're having a language recognition problem here, we said, okay, we'll use a finite state machine, a finite automaton. And one important aspect of that is we are using a model for the clean files. So we're not putting any understanding of what the method looks like that the malware will use into this. We're just putting the understanding that we gain from the training data. So we're matching against a model for clean files. We're not matching against a model of particular malware or data exfiltration methods. And here, well, it's pretty straightforward. We'll have a state for each segment type, and we'll have directed edges for segments that were observed in a given order. And then we add some annotations to these edges. So when the segment has a fixed length and strictly fixed length, then we just count how many times we've observed it during the training phase. And when the second segment is of variable length, we store the distribution of lengths that we observed during the training. And as you can imagine, when you have something like byte stuffing, observing the length of the segments is an important factor, because here we have a legitimate segment observed in the legitimate order, and the only thing that may distinguish the file from legitimate files is the fact that the segment is larger than usual. So this is basically what we do here. We take into consideration the newly observed length. That would be, for instance, the solid green line. And then we create a radius, basically, using this factor alpha, and so that we have a range around the observed value, and then we just count how many observations did we have in the training phase in that range. And if that's more than tau, then we say, okay, we're good. We have a good impression that this is valid with respect to our approximate model. If, on the other hand, we have something like in the red case, there are few observations in the training phase that fall into that area, then we assume that this is illegitimate. Okay, so now obviously we wanted to know whether we've built something that really works. And getting back to the model, we thought, okay, so how can we get as close as possible to what, let's say, web application firewall would see in such a scenario. So what we did is we recursively crawled the Alexa top 25 domains, and we stored all the image files that would be downloaded in the process. So we ended up with about 300,000 image files, 270,000 of which are JPEG and 43,000 PNG. So we expect this is an indicator of how widely used these formats are, but it was not the intention of our work. Then we did a 10-fold cross-validation, and for our test set, well, we had obviously left some unmodified files in there so that we could determine the false positive ratio. Additionally, we had some live images from malware. We also, for the ZeusVM, we also had a builder kit for building the configuration, so we used that as well. And yeah, so as you know, there are quite a few malware families that are actually using these techniques. And from those, we selected those where we had a good understanding not only of how the method works, but also of the payload that the malware is injecting, so that we could actually pretty closely resemble where we had to generate the data set, what the malware communication or the file that we were used for malware communication looked like. And one funny thing, like basically by chance in the process, we found that stack detect, so the prototype implementation of for a paper that Niels Provost wrote almost 20 years ago, and the paper was on JPEG image database detection. The prototype also contained some methods that were designed to allow structural detection, and the nice thing about it is that it gives you basically a baseline to compare our method against, at least for JPEG files. Another aspect which is really important, in particular with respect to stack detect, is other than we expected, our base data set contained a large number of files that already contained data behind the end of image segment. So as you can see here, there were 5,000, about 5,000 files, JPEG files that contained some extra data, and also 300 PNG files. Plus, there was one particular site, I'm not pointing any fingers, that almost doubled these numbers. So we have a fraction of about 5.5% for Twitter, and about 2.6% for PNG file, sorry, for JPEG, and about 2.6 for PNG, where the image files in our base dataset already contained residual data. So for JPEG, we use these malware families. As you can see, there's a strong focus on malware that uses the append paradigm. That's actually also used by a large number of pretty high-profile APT malware. As you can see, the ZeusVM banking trojan is using the injection approach. However, the files that it creates are in a sense broken. So we added another approach which uses the injection paradigm, but creates files that are not broken. And then we didn't see any byte stuffing based approach, so we designed our own to be able to check whether our method's actually able to detect that. So, well, starting with the true negative ratio on the left, so if the green boxes are for SADFUG and the blue ones are for stack detect, you see that SADFUG is like in the 99 point something area with respect to true negatives. And actually, so stack detect here is hindered by this fact that I just pointed out, that there is actually quite a lot of image files with extra data behind their end of image markers. So that's a problem for stack detect. For SADFUG, well, we learn how files are supposed to look like, and that compensates a little bit for that. When you look at the malware families that use the append approach, well, okay, I think you can argue that stack detect is actually having a 100% true positive, because you see there these error indicators at the bottom, and actually these correspond to files that were grayscale, and the application simply couldn't parse grayscale images. So the approach was just basically just a signature on are there more than 3 bytes behind the end of image marker. I would say that would have identified all of these correctly. Where for SADFUG, we have some very nice results, obviously. But also there are some approaches for which the performance is a little bit degraded by the fact that we are learning that to some degree extra data behind the end of image marker is normal. When we look at the other approach, however, well, the performance of stack detect basically goes to 0, and StatFuck achieves 100% true positives. So you may argue, obviously, that for the app 0 and so the methods that we introduced, stack detect is actually having some true positives here. However, the problem here is that these are, so what stack detect is attacking is the extra data and the base files that we were using to create those images. So if that data weren't there, the detection of stack detect would not trigger, and that's why if you think you can argue that these are actually false positives. So for PNG, well, we had 3 malware families. We added 2 more methods, one injection-based approach and one byte-stuffing approach. As you can see, there's the CryLocker, which basically uses a variation of the byte-stuffing approach. And again, that was a malware that creates broken files, and we thought, okay, we should really have a sample that does not create broken files here. I don't have any base for a comparison here. The true negative ratio is a little lower here, so we are in the upper range of 98%, going a little bit above that, so in the 99% area. But we have a smaller training set, so probably that's the reason why we don't capture all the commonalities of the file format. Again, for the injection-based approaches, we have 100% true positive, which is of course very nice. However, again, we see this effect of the residual data in the base set that degrades the quality for the append-based approach a little bit. But then again, for the byte-stuffing approach, we have 100% true positives. So to wrap things up, so setfuck makes fuck set. And structural embedding methods are basically as prevalent as image database methods. So it's, at least when you look at malware, that's a problem that seems to have been overlooked for a while. And the nice thing is that, well, we think we're providing a very good method for detecting them. And since we're using a model for the files without any embedding, we also think that it's capable of detecting anything that we didn't think of, as long as it has an effect on the structure of the files. And yeah, that's basically the last point. So there's the only limitation is that, well, you have to have a structured file format, and you have to be able to parse it into a format that we can process. So thank you, and I think we have a little time left for questions.
In fact, we have plenty of time for questions.
Oh.
While people coming up to the mic, I have one question for you. I think this is interesting finding, and I also truly believe that your approach and direction in general can identify majority of those cases in real world. But as James pointed out in the keynote, do you have any concern about using machine learning in security in general?
Sorry?
Do you have any concern about using machine learning in security in the context of your work?
Yes. So actually, I mean, there's some in the paper you'll find some words on how poisoning could affect this approach, and that's reasonable to assume that an attacker which has, or basically for any machine learning based approach, if you control the training data, you're controlling the detection result. So we came up with a few designs which we didn't implement for limiting the effect of an attacker that has, well, at least partial control over the training data. Obviously, when the attacker has full control over the training data, you kind of work. But I mean, getting back to James' example, so I think the problem with Tay is that they were continuously learning, and this is an approach where we would say, okay, we have a curated set that we're learning from, and then we'll keep it. And if the quality of the detection degrades for our purposes, then we'll have to create a new curated set to be able to detect.
If there is no one, I have another question for you. what if you're an attacker? What is the best strategy for you to bypass your classifier that you have?
Well, most obvious approach is just to, since this is only looking at the file structure, you can use image database. We are aware that this will not get the capacity of the channel down to 0, because obviously, when you look at this slide, for instance, you could add a few bytes here on, let's say, the left side where you have the green indication. However, so when you have a, let's say, image database approach, usually you have, let's say, a few bytes for each packet that you send. And what we think with the right configuration, you will get to a similar low level of bandwidth, actually. So for the attacker, this is basically makes the channel very uninteresting. Or let's say without this method, you could really use one single image file to transfer a gigabyte of data. And as long as you don't have any detection method that takes that into consideration, you'll not be able to understand that fact. And with this, well, you get somewhere in the area where you could at least consider switching to image database methods, or, well, basically, there are always other methods. If you look at the work of Mordechai Guri, he's lots of very interesting but low bandwidth channels for data exploitation.
Great. Let's thank our speaker once more.